Now we come to chapter 3, module 5. In this module, we shall continue to study Fredholm integral equation of second kind with continuous kernel and forcing function. Here we shall see how a degenerate kernel can be associated with continuous kernel, so that the theory of Fredholm alternative can be applied to Fredholm integral equation of second kind with continuous kernel. Let us consider the integral equation as given by equation 3.55. Here the kernel function kxt and the forcing function fx are continuous functions. This integral equation can be written in the operator form as I minus lambda capital K phi equal to f. Here capital I is the identity operator and capital K is the linear integral operator given by K phi x equal to integral from a to b kxt phi t dt. Now we have already seen in chapter 3 module 1 that the integral equation 3.55 has unique solution in the form of Neumann series given by phi x equal to fx plus lambda summation n equal to 1 to infinity lambda to the power n minus 1 phi superscript n x, where the function phi superscript n x is equal to integral a to b kxt phi superscript n minus 1 t dt, which is in the operator form can be written as capital K phi superscript n minus 1 x. This is the operator form. Here phi superscript 0 x is fx, and this Neumann series solution exists provided the parameter lambda satisfies the condition given by equation 3.56, where capital M is the supremum of the function mod kxt, x and t both are varying in the interval ab. We have also seen that the Neumann series solution can be alternately represented in the form of iterated kernel given by equation 3.57, where the iterated kernel knxt is equal to integral from a to b kn minus 1 xs into kst ds, n is greater than equal to 2, and k1 xt is the kernel kxt, provided the condition given by 3.56 is satisfied. Now we shall show that the condition given by 3.56, that is mod lambda capital M into b minus a less than 1, can be replaced by the condition given by equation 3.59, where the symbol, this symbol is the norm of the function kxt, and it is defined as double integral from a to b mod kst square ds dt as given by equation 3.60. Now we shall derive this condition. To derive this condition, we apply Cauchy-Schwarz inequality in the following manner. We consider this function, that is the integral a to b kn(xt) ft dt on the right hand side of equation 3.57 and take the mod value of this and square. This becomes less than equal to integral of a to b mod kn(st) square dt into integral of a to b mod ft square dt. This is obtained by applying Cauchy-Schwarz inequality. Now, the integral a to b mod ft square dt, this is a constant and we denote it by capital T square, and the other integral we write dn square as the upper bound of the other integral from a to b mod kn st square dt, s lying in the interval a to b. So with this assumption, equation 3.61 becomes the left hand side is less than equal to capital T square into capital Dn square, which is given by equation 3.62. Now again we apply Cauchy-Schwarz inequality to equation 3.58, that is this equation. So if we apply Cauchy-Schwarz inequality to equation 3.58, we see that mod kn xt square, this is given by mod of this integral square, and applying Cauchy-Schwarz inequality we find that this is less than equal to integral a to b mod kn minus 1 xs square ds into integral a to b mod kst square ds. Now we will integrate this with respect to t from a to b. So left hand side we integrate, left hand side, that means mod kn xt square we integrate with respect to t from a to b, and on the right hand side in this expression, here there is, in this expression there is no t and there is t in this expression. So we integrate this expression with respect to t, so that the left hand side is integral a to b mod kn xt square dt, and right hand side is capital Dn minus 1 square into norm of k2 square, because this has got t, so double integral a to b mod kst square ds, this is norm of k2 square as defined in equation 3.60, and dn square is the upper bound of this integral, so that dn minus 1 square is the upper bound of this integral. So combining this result, we get this result. Hence, we can see that the left hand side of this inequality, that is integral a to b mod kn xt square dt, this is less than equal to dn minus 1 square into norm of k2 square for all x in the interval a to b. Hence, its upper bound is also less than the right hand side. Recall that the upper bound of left hand side is dn square, so that we obtain dn square is less than equal to norm of k2 square into dn minus 1 square for n greater than equal to 2. Similarly, we can prove that dn minus 1 square is less than equal to norm of k2 square into dn minus 2 square. If I use that in this inequality, we get dn square is less than equal to something which involves dn minus 2 square. So this inequality sets up a recurrence inequality, and we continue in this way to obtain dn square is less than equal to norm of k2 to the power 2n minus 2 into d1 square. Hence, from 3.62, that means from here, we see that dn, we have set up recurrence inequality for dn square. So if I substitute that inequality in this equation 3.62, we obtain that mod of integral a to b kn st ft dt whole square less than equal to t square d1 square into norm of k2 to the power 2n minus 2. That means we have got an estimate of the expression on the left hand side. Now, from this relation, we find that the infinite series on the right hand side of equation 3.57, that is this expression, will converge absolutely and uniformly if mod lambda into norm of k2 is less than 1. So this we are to show, and we have shown this here. We now make following observations to derive three important theorems called Fredholm theorem. First of all, we shall show that how a degenerate kernel can be associated with the continuous kernel of the integral equation of second kind. Now we come to remark 1. We know that if kxt is a continuous function in the square AB cross AB, then kxt can be expanded in Fourier series in terms of complete orthonormal set of continuous functions Bix, I ranges from 1 to infinity, in the closed interval AB in the form given by equation 3.63. So kxt has the Fourier expansion as given by equation 3.63, where the functions aix are called the Fourier coefficients, which are given by aix equal to integral a to b kxt bi bar t dt as given by equation 3.64. Now we come to remark 2. The well-known Parseval's relation for Fourier series 3.63 is given by summation I equal to 1 to infinity mod aix square is equal to a to b mod kxt square dt as given by equation 3.65. Now we integrate both sides of equation 3.65 with respect to x from a to b, and we note that aix and kxt are both continuous functions, so that the summation and integral can be interchanged to get the relation given by 3.66. Now the right hand side of relation 3.66, that is the double integral mod kxt square dx dt, it is finite. So the left hand side, that is summation I equal to 1 to infinity a to b integral mod aix square dx, this is finite. So this shows that this infinite sum, if it is finite, that means we can say that given sufficiently small positive number epsilon, there exists sufficiently large positive integer capital N such that for all small n greater than capital N, the remainder in the series on the left hand side of equation 3.66, that is summation I equal to n plus 1 to infinity integral a to b mod aix square dx, this is less than epsilon square, say, where epsilon is a very small positive number as given by equation 3.67. Now we must remember this result and come to remark 3. If phi nx, n ranging from 1 to infinity, is a complete orthonormal set of continuous functions in the closed interval ab, then we can expand any continuous function phi x in the closed interval ab into Fourier series as phi x equal to summation n equal to 1 to infinity Cn phi n x as given by equation 3.68. Here the Fourier coefficients Cn's are given by Cn equal to integral from a to b phi x phi n x bar dx. Here bar denotes the complex conjugate. Now come to equation 3.68. The series on the right hand side of equation 3.68 is an infinite series. Now we can rewrite this series as summation n equal to capital N plus 1 to infinity Cn phi n, this is equal to phi x minus summation n equal to 1 to capital N Cn phi n. So that we consider the expression integral a to b mod of phi x minus summation n equal to 1 to capital N Cn phi nx square dx. This can be written as integral a to b phi x minus summation n equal to 1 to capital N Cn phi nx into its complex conjugate, that is phi x minus summation m equal to 1 to capital M summation m equal to 1 to capital N Cm phi mx bar dx. Now, from this result, we can write this expression as summation small n equal to capital N plus 1 Cn phi nx. So that next step is integral a to b summation n equal to capital N plus 1 to infinity Cn phi nx into phi x minus summation m equal to 1 to capital N Cm phi mx bar dx. Now, if I multiply the two expressions here, we get for the first term summation small n equal to capital N plus 1 to infinity Cn into integral a to b phi nx into phi x bar, and that will be equal to Cn bar as given by equation 3.69. So, for the first term in this multiplication, this will be Cn into Cn bar, that will give you this expression mod of Cn bar square summation, where small n ranges from capital N plus 1 to infinity. Next comes, if I multiply this term with this term, and that gives double summation small n equal to capital N plus 1 to infinity Cn into summation m equal to 1 to capital N Cm bar integral a to b phi nx into phi mx bar dx. Now, recall that phi nx, these are the orthonormal set of functions. That means the integral phi nx into phi m bar x dx, that is equal to 0 for m not equal to n and equal to 1 for m equal to n. So, if I use this result in the second term on the right hand side, we see that n, small n ranges from capital N plus 1 to infinity, and small m ranges from 1 to capital N. So, m is not equal to n, so this integral is 0. So, this whole term vanishes and we are left with only summation n equal to capital N plus 1 to infinity mod Cn square in the right hand side, and left hand side is this function as given in equation 3.70. So this result we will use later on. Now recall the remark 1. In remark 1, we have told that if kxt is a continuous function, then it can be expanded in Fourier series in terms of complete orthonormal functions BIT. So if I use this result 3.70 and use kxt in place of phi x and the expansion for kxt as shown in remark 1, then we can get the result as given by 3.71. Now I integrate both sides with respect to x from a to b, and if I note the relation 3.67, that summation I equal to n plus 1 to infinity integral a to b mod aix square dx, this is less than epsilon square. If I use this result, then we find that after integration, that is, this expression is less than epsilon square. This is given by equation 3.72 whenever small n is greater than capital N and capital N is sufficiently large positive integer. So the above result 3.72 shows that the given continuous function kxt can be approximated by this function, that is this series, as given in 3.72. So in other words, we can say that kxt can be approximated by the function pxt, which is the series summation I equal to 1 to n aix into bit as given in 3.73. That means kxt can be approximated by the function which contains a finite sum for sufficiently large n, which produces the inequality given by equation 3.74 for a arbitrarily chosen positive number epsilon. Now we come to remark 4. So we have seen that the function, continuous function kxt can be approximated by a finite sum as given by equation 3.73, so that we can write kxt equal to pxt plus qxt, that is qxt the error term here, so that the result 3.74 on the left hand side, this function can be written as double integral a to b mod qxt square dx dt, and that is the norm of q square, and which is less than epsilon square, that is norm of q is less than epsilon as given in equation 3.76. Now we note this result 3.75 and we express the given integral equation 3.55, that is phi x equal to fx plus lambda integral a to b kxt phi t dt as phi x equal to fx plus lambda integral, instead of kxt we substitute pxt plus qxt into phi t dt. Now we take this term lambda into integral qxt phi t dt to the left hand side, so that this gives the equation given by equation 3.77. So if I say the function on the right hand side is equal to f1 x lambda as given by equation 3.78, then we can write the equation 3.77 in the operator form as I minus lambda q phi x equal to f1 x lambda, where the integral operator q phi x is given by integral a to b qxt phi t dt. This integral, this term we write as capital Q phi x. So equation 3.77 is the integral equation whose kernel is qxt, and we have seen earlier that the unique solution of this integral equation will exist, or in other words, the inverse of the operator I minus lambda q will exist uniquely if mod lambda into norm q2 is less than 1. Now in relation 3.76, we have seen that norm q2 is less than epsilon, so that the inverse operator I minus lambda q inverse will exist whenever mod lambda norm q is less than mod lambda epsilon, and that is less than 1. So mod lambda should be less than 1 by epsilon as given by equation 3.79. Also, from chapter 3 module 4, we have learned that the solution of the integral equation 3.77 associated with the kernel qxt can be expressed assuming as though f1 is known, that is the right hand side is known, in the form given by equation 3.80, where rqxt is the resolvent kernel in this case. Now we substitute the value of f1 x t lambda in the integral equation 3.80 to get a long expression given by this. Now if I write this fx plus lambda integral a to b rq xt lambda into ft dt as f to x lambda as given by 3.82, then this expression can be alternately written as phi x equal to f to x lambda plus lambda integral pxt phi t dt plus lambda square integral rqxt lambda into integral pts phi s ds dt as given by equation 3.81. Now we know that pxt is the finite sum of ai x into bit. We substitute pxt in this expression 3.81 to get a long expression as given by this. We can note here that the function f2 lambda is equal to 0 whenever fx is equal to 0 as seen in equation 3.82. Now this long expression here can be rearranged by interchanging the order of summation and integration to obtain phi x equal to f to x lambda plus lambda integral a to b summation I equal to 1 to n aix plus lambda integral rq xt lambda ait dt into bis phi s ds. Now if I write the expression in the second bracket here as yix as given in equation 3.83, then this expression becomes phi x equal to f2 x lambda plus lambda integral summation I equal to 1 to n yix into bis phi s ds. This can be alternately written as phi x equal to f2 x lambda plus lambda integral a to b L xt lambda phi t dt, where L xt lambda is the finite sum I equal to 1 to n yix into bit. Now if I compare integral equation 3.84 with the given Fredholm integral equation, we see that this L xt lambda we can be identified with the kxt there, and this L xt lambda, that is the kernel of this integration 3.84, is expressed as degenerate kernel as given by equation 3.85. So we have seen that the integral equation of second kind with continuous kernel can be associated with integral equation with degenerate kernel based on the remarks 1 to 4. So with this idea, we state three definitions and three theorems known as Fredholm theorems. Definition 1, lambda is called a regular value of the operator capital K if the integral equation 3.55, that is the given integral equation, possesses unique solution. Definition 2 is lambda is called the characteristic value of the operator capital K if homogeneous equation corresponding to given integral equation 3.55, that is I minus lambda k phi equal to 0, possesses non-trivial solution. The adjoint operator capital K is defined by k star phi, that is equal to integral a to b k t x bar phi t dt. We may note here that k star equal to k implies kxt equal to ktx bar, where bar is the complex conjugate, and if this happens, then the kernel kxt is called the Hermitian or self-adjoint. Now we come to three very important theorems known as Fredholm theorems. Theorem 3.1, if K is an integral operator with a continuous kernel kxt and I minus lambda k phi equal to f is a Fredholm integral equation of second kind, then lambda is either a regular value or characteristic value of the operator capital K. And the set of characteristic values are countably infinite in number. Next comes theorem 3.2. If lambda is a characteristic value of capital K, then lambda bar is a characteristic value of capital K star, that is the adjoint operator. The number of linearly independent solutions of the homogeneous equation, that is I minus lambda k phi equal to 0, and the adjoint homogeneous equation as given by equation 3.86 are the same. The last theorem 3.3 is if lambda is the characteristic value of capital K and f is a continuous function, the integral equation 3.55, that is the given integral equation, has either no solution or non-unique solutions if f is orthogonal to every continuous solution of the adjoint homogeneous equation 3.86. So, in this module we have seen that Fredholm integral equation of second kind with continuous kernel can be associated with Fredholm integral equation with degenerate kernel. And through three Fredholm's theorems, we have seen that Fredholm alternative can be applied in case of Fredholm integral equation of second kind with continuous kernel.